Welcome everyone. Today we will be introducing you to SELENE. Named after the goddess of the moon, it will be exploring the technologies that may give way to permanent settlements on the moon. The SELENE rover is scheduled to fly to the lunar South Pole in 2023 as part of the Artemis program. It was developed by the Morehead State University from Kentucky and the Delft University of Technology from the Netherlands. As a transatlantic cooperation, the expertise of both is applied. Morehead has already gained a lot of experience from their lunar IceCube mission, which will search for water from lunar orbit in 2021 on board the Artemis 1 mission. Delft brings know-how from their experience in building scouting rovers to the table. Before getting into the more technical details, Becca will discuss the relevance of SELENE. This gives rise to our primary payload, the GCMS, which is one out of 4 onboard payloads. Further, she will discuss the concept of operations. To power all of these systems, energy has to be generated, stored and distributed. Aart will discuss the power system that takes care of this. The more technical details of the scouting rover and the arm will then be reviewed. With all of this established, Titi will consider the secondary science payloads. A lunar seismometer is implemented to lay the foundations of moon-based building. Further, LUFAR, an antenna for radio astronomy, is enabling us to take high-resolution images of extremely faint signals coming from old distant sources. Lastly, there is the loop. Able to study reflected polarized light from Earth, it can set standards for future direct observations of exoplanets. Then, the last technical details of the rover can be taken into consideration. Justin will explain how the locomotion system makes the rover move to any location and how the thermal system makes sure that all different subsystems stay within their operating temperature range at all times. Lastly, he will discuss how the communication system enables contact between the rover and either astronauts on Gateway or the ground station on Earth. That will then conclude this presentation, and now I give the word to Becca.
Thank you, Peter. SELENE has one of the most unique concepts of operations proposed until now. Our primary science goal is to confirm the presence of water ice at the lunar South Pole from lunar IceCube missions mapping efforts. SELENE employs a unique concept that will utilize 2 different types of rovers over the course of the mission, a mother rover and 2 scouting rovers. The mother rover will be the location of the primary and secondary science payloads, as well as the rover that the astronauts will use. The mission will take place in 2 phases. The first phase will be completely remote and autonomous. In this phase, the scouting rovers will guide the mother rover to areas of interest and will be able to return to the mother rover to charge their batteries and/or for maintenance. The second phase will be a crewed exploration where the rover will hold 2 astronauts. They will be able to drive the rover and operate all of its payloads from the cockpit. As I said before, one of the primary mission objectives is to follow up the lunar IceCube mission by confirming the presence of water ice on the surface of the lunar South Pole. So one of the things we know is that water transfers over the lunar surface through physical mechanisms. And the goal of lunar IceCube is to see, how do these physical mechanisms take place? Do they change with time? Do they change with illumination angle? These are all big questions we have that SELENE could help answer. We will accomplish this through the use of a gas chromatography mass spectrometer, or a GCMS. The GCMS is the most popularly used analytical chemistry tool on Earth today. It has been designed over the course of decades to be accurate, powerful, and fast. They have been designed to be used in lab settings, and field work settings, and in teaching settings. However, this design has left them really poorly equipped for space exploration. They are large, heavy, require a lot of power, and they require sample injection in a liquid form through a capillary needle. We propose a GCMS system to mitigate these issues. We will use a GCMS derived from the Griffin 510 GCMS for field work. It is compact and lightweight at 37 by 37 by 40 centimeters and weighing in at just under 16 kilograms. We propose to use a version of this instrument made of space-grade materials as our primary payload. In addition to increasing durability and environmental range throughout the instrument being constructed from space-grade materials, we have a sample input system that does not require injection, which is one of the biggest factors in why you might not want to use a GCMS, but we propose to take a note from Viking. We want to take 2 ovens that heat samples of 1 gram to 500 degrees Celsius over the course of only a few seconds. These samples will then bake out all of the possible volatiles and waters and organics within, and will then flow into the GC column through the use of capillaries and valves. So once the oven gets to 500 degrees Celsius, these valves will click and the sample will be distributed onto the column. One of the primary risks in using a GCMS is overloading that column. The column is very, very small. Sometimes they're only a few human hairs in diameter. So once you overload them, that column can never be wiped clean, it can never be fixed, and you lose a lot of resolution, you use the ability to identify small compounds, and a lot of the lines that you would get tend to blur together. We suggest a way to prevent this from happening in the first place. So I mentioned before that we're only going to be using a gram of sample, and that's because even a gram of lunar regolith would only contain probably between 10 and 20 microliters worth of volatile samples once baked out. So these lunar regolith samples will be collected with the use of a robotic arm. Samples will be collected at a depth of 10 to 30 centimeters, and this depth is necessary to avoid exposure to UV light, which can act to sublimate water ice from soil samples as well as degrade any possible organics that we might find. While water ice may be our primary science goal, finding organics and identifying minerals in lunar regolith can be secondary and tertiary goals that we can work towards. The arm will only need to collect a small amount of sample. As I said before, too much will overload the GCMS. An onboard drill will loosen frozen regolith and make collection at subsurface levels possible. The samples collected will be deposited into the top of a single oven through a port that seals and unseals as necessary. Now I'll pass it over to Art, where he will discuss power requirements for our system. Thank you.
First, I will discuss the power system, which supplies all parts of the rover with energy. It is divided into 3 parts, taking care of the generation, the storage, and the distribution of energy. To produce energy on a remote location, such as the moon, solar cells are a straightforward option. Efficient and reliable quadruple junction gallium arsenide cells are implemented. These currently have a TRL of 9, which makes them perfectly suitable. It is important to realize that on the south pole of the moon, solar rays are almost parallel to the surface. This means that the solar cells have to be placed perpendicular to the ground. As you can see, the solar panels of both sides are turned towards the back of the rover during charging, ensuring its full capacity is used. However, when the solar cells are not in use, they can be contracted into the rover. This protects them from phenomena such as permanent dust cloud that is present on the moon. Since energy is not immediately used after generation, it needs to be stored for later use. This is made possible by the regenerative fuel cell. It was chosen over batteries for 2 important reasons. First, since minimizing weight is essential for launch, a higher energy density is an important factor. Fuel cell systems can store up to 3 times more energy than batteries with equal weight. Further, since the presence of water on the moon has been established, fuel cells have sparked particular interest, as water can be converted into hydrogen and oxygen. If successful, the use of a fuel cell can thus give rise to a new era of space exploration, and this rover can be the proof of concept. This prototype was created by our team to show the use of a reversible fuel cell for the SELENE rover in a simplified way. The solar panel on the left converts the solar energy into electricity, which powers the reversible fuel cell. The fuel cell will transform the water into hydrogen and oxygen, which is stored in 2 tanks. The oxygen and hydrogen are then used to power the second fuel cell, which in his turn powers a small DC motor. The black circuit board with the SELENE logo showing measures the voltage and the current on the fuel cell, and sends the data to a microcontroller on the right. This microcontroller is connected to the computer to do the post-processing on the data. The screen shows the input and output power, voltage and current, as well as the efficiency. The model is fully operational and was used to study different behaviors of the fuel cell. On the rover, a unitized fuel cell is used, or a URFC. The unitized stands for the fact that a fuel cell operates in 2 directions, both charging and discharging. This again saves mass as opposed to the system that's currently in place. One of the main issues that still remain when implementing a URFC is a drop in efficiency, due to clogging. Water can flood the membranes when switching modes. Because the capacity of the rover is very high, mode switches are not that frequent. This resolves most of the problems. Furthermore, Different types of solutions are being tested, as this is an active research topic. The power distribution system has 4 voltage levels, ranging from 3.3, which we use for sensors, to 24 volts, for example for the locomotion system. This supplies every component. An important addition here is the extra battery, which has 3 functions. The batteries can deliver power to the distribution system during the brief mode switches to protect sensitive components. Further, it can apply short power bursts which can be needed for large loads on the arm or the locomotion system. And lastly, it acts as a safety buffer. In the unlikely case that the fuel cell would malfunction, the rover could go into hibernation mode and survive a lunar night, after which it can charge again during the day. The navigation system consists of 2 parts, operating at a global and a local scale. The global localization system can determine the exact location of the rover on the moon, when the navigation, the D-star path planning algorithm is used to determine the broad direction of where the rover is going. On a smaller scale, the local system comes in. A collection of sensors, including a radar and a proximity sensors, deliver a 360-degree view. This ensures all potential threats can be detected and avoided. Using the monocular and stereo vision, a 3D map of the surrounding can be generated and used to navigate around threats and obstacles. The same method is used for the scouting rovers. These rovers are based on the design of the lunar zebra that is created by a student team at the TU Delft, as already mentioned. They weigh around 2.5 kilograms per rover and can overcome 50mm obstacles. These rovers can be used to look for water or scout dangerous terrain. They can charge themselves using their solar cells, or this can be done by the mother rover. With a communication radius of 5 kilometers, they can perform their own measurements in a self-sufficient way. The arm that is located on the front of the rover works in a similar way as a human arm. It has a shoulder, elbow and a wrist. The main purpose is to collect the lunar regolith for the science payloads. Lights and a high-definition camera help guide the arm and precisely position it for picking up lunar regolith and other tasks. The arm is also responsible for deploying the scouting rovers and storing them on the top deck of the mother rover. To not harm the scouting rovers, but more importantly the human crew, several safety sensors are in place. Also, the arm can carry loads up to 150 kilograms, which is very useful to deploy infrastructure and help astronauts with unloading. Lastly, the arm is able to get rid of some of the dust on the solar panels as well as the chassis, which will increase the longevity. Now I will hand it over to Titi, which will tell you about the science payloads.
Thank you, Art. As we all dream of building a moon base for our future deep space missions, it is vital for us to know whether the required structures can be built or not. Therefore, studying lunar seismology helps us learn about the properties and composition of the internal structure of the moon, also helping us assess and reduce the dangers from natural hazards. For that reason, one of our payloads is regarding seismology. The Apollo seismometers have unveiled a lot of crucial information like composition, structure, including the fact that moonquakes are not caused by tectonic events but by tidal forces. However, seismometers were placed on the equatorial strip. Thus, we will be using several high-precision, ultra-compact seismic sensors on our rovers to record the seismic activity on the South Pole. These are 3-axis acceleration sensors from Omron, model DS7A0001, in the range of -20 meters per second squared to +20 meters per second squared. Hence, it can record the data over the entire Richter scale. A sensor is placed under each of the dotted rovers, and a third is attached with the telescopic arm under the mother rover, protected by a casing. The casing safeguards the sensor from radiation and temperature changes, preventing malfunction from environmental factors. Thus, the seismic activity will be recorded during the standing and recharging hours of the rover. Now, for our next payload, we have LUFA.
that is lunar low-frequency antennas for radio astronomy. Having a mother rover and 2 daughter rovers gives us this advantage of creating the perfect 3-node setup in a Y formation for the radio astronomy. Each of the rovers is equipped with a 1-meter-long low-frequency synthetic aperture radio, whose range is from 30 kHz to 30 MHz. Low-frequency radio astronomy cannot be done from Earth due to atmosphere. Ionosphere can cause severe issues, and ionospheric phase corrections do not work under 30 MHz due to ionospheric scintillation. Thus, having it on lunar surface allows us to look at unexplored, extremely faint signals coming from old distant source in high resolution. Additionally, it is considered that Moon can be used as a shield from radio frequency interferences produced by the Earth. This concept was unveiled by Explorer 49 in 1943, in consequence providing us with precise results. LUFA also enables us to acquire very useful information on the low-frequency RFI environment on the Moon. This setup takes measurements in increments of 50 meters distance, but there is one limitation, that the baseline cannot be more than 5 kilometers because of the low power availability on daughter rovers. Another payload on board is LOOP, Lunar Observatory for Unresolved Polarimetry of Earth. LOOP measures the reflected polarized light from Earth, which aids us to set a standard reference data for future direct observations of exoplanets. LOOP is an ultra-compact spectropolarimeter designed to measure reflected flux and polarization spectrum of Earth, and Moon is at an appropriate distance to provide an instantaneous view of entire Earth's disk, which might be tricky to obtain from a stationary satellite. Now Justin will continue with the thermal and communication parts of the rover.
Thank you, TD. SELENE's structure is derived from a conventional car. This design makes SELENE flexible for different mission objectives when time progresses. As the structure of SELENE is essential in protecting the astronauts against possible collisions, I-beams are placed at the base of SELENE. These I-beams are able to absorb massive amounts of energy in combination with the crumble zone. A unique feature of SELENE are the ceramic matrix composite panels. The CMC panels are able to retain their very high modulus at temperatures of 1000 degrees Celsius. The CMC panels also provide a shield of environment for the sensitive instruments. So, the instruments are protected against solar radiation and lunar dust. The cockpit has a user-friendly interface. Multiple interactive touchscreen displays provide all information of SELENE. 2 multi-purpose joysticks provide the means to command SELENE's driving system, interface system, and the instruments available on SELENE. Further, a pad in the middle of the cockpit provides manual switches, for example, the switch between driving mode and operating mode. To make sure that SELENE's cockpit is clean when astronauts arrive, is the cockpit covered when SELENE is driving remotely. In addition to SELENE's structure, is the relatively low center of gravity. The advantage is that SELENE is unlikely to topple when driving over steep slopes. The thermal regulation system distributes heat through SELENE to give thermal support for the subsystems in SELENE. The thermal system has 2 subsystems, a passive and an active thermal system. The passive system is able to absorb redundant heat using a phase-changing material, PCM in short. Lithium hydride is used as a PCM in SELENE due to lithium hydride having a high latent heat of fusion with a value of 1600 joules per kilogram per Kelvin. A heat loop system circulates the heated PCM to a subsystem, which requires thermal support. If SELENE's passive thermal system is not able to distribute enough heat to the designated subsystem, the active thermal system will give additional support to ensure that optimal temperatures are preserved. The active thermal subsystem consists of a heat generator and a radiator. The radiator emits the generated heat, where nearby heat loops filled with PCM are able to absorb this heat. The CMC panels have a low thermal conductivity and are able to heat up to 1000 degrees Celsius while letting a low amount of heat through the 2mm thick plate. This property makes the CMC panel a good insulator for SELENE. As a result, is SELENE thermally a very efficient rover.
Thank you, Justin. We have now seen all subsystems. These should equip the rover to strongly contribute to the renewed interest in the moon. In total, everything weighs 292 kilograms with a total cost of less than $300 million US. The rover has 4 onboard payloads and can be used by a crew of up to 2. The power system, which will be proving the capabilities of regenerative hydrogen fuel cells, can generate up to 1.5 kilowatts. This can make the rover move at a speed of up to 8 meters per second or 30 kilometers an hour. The maximum range of one charging cycle is 60 kilometers, and the design of the rover allows for a minimum lifespan of 2 years. SELENE gives an excellent opportunity to follow up on the discoveries made by the Lunar Ice Cube mission. This will be done by examining candidate locations for water to be used in future missions and by confirming ground truth. This will be done using the onboard instruments and with the help of the scouting rovers. This brings us to the end of our presentation. We hope it has been clear and interesting for you and that you may walk away with a broadened view of the opportunities and prospects of future space travel. Thank you for watching, and we would be happy to answer your questions.